We have got to work so hard to wow you. We've got some amazing pictures coming up in the next hour. We won't get through all of them, but I hope that at the end of this you'll be just amazed by what astronomers can do at the moment. So I'm Roland Pease. I work for the BBC. I report on things like the James Webb Space Telescope. In the past, I talked about the Hubble Space Telescope, which is actually still up there taking pictures as well. If we can introduce then our two guests. The great sadness is that I'm here with you lot, and the really important people are behind me. They're zooming in. First of all, can I introduce on the right, Heidi Hammel is one of the most amazing astronomers I know. I first spoke to Heidi, I don't know if she remembers this, in about 1994, I think it was. I was making a program about planets, and we speculated about the ideas that there may be planets beyond our own solar system, and at that time we didn't know any. I mean, how many do we know now, Heidi?
Over 5,000 planets now, Roland.
I think about 2 weeks after I spoke to Heidi, we discovered the very first one, or I didn't, they did, the very first one. So Heidi is at the AURA, you better spell that out for me.
Association of Universities for Research in Astronomy.
In other words, you're the czar. You control all of the telescopes, or most of the telescopes. You pull strings for all the astronomers in America.
Well, we don't pull strings, but we make all of the United States large telescopes in space and on the ground available to users around the world.
Yeah, I think that's pretty big. So Heidi does an amazing job also, not only of sort of running the telescopes, but of also telling people about it. The other person I did not speak to until 2 days ago. This is Tom Williams, who only on Thursday, there was the latest release of some amazing pictures from James Webb. I saw the pictures, they blew my mind. I basically called up Tom and said, could you come and talk to us about this stuff? You would like to be here, Tom, but you've got other things to do.
Yeah, unfortunately, yeah, I can't be there today. I do live in Swindon now, so...
You do, but you're meeting your family?
On the road. Yeah, I'm visiting my mum this weekend because me and my partner, who is hiding behind me, just got engaged last week. So
big round of applause, please. So otherwise, Tom would have been here to share this with us. Let's go to before just one other thing, Heidi. Just show us your cup of coffee. It's only quarter past 7 in Washington, D.C., which is where she's talking to us from. We are so privileged that she agreed to do this, and she got up unbelievably early to make sure that the connections all worked. I'm going to come up and sit up here. If we can turn over to the slideshow, because actually I want to see the pictures as well. And I've got a microphone. As we go through these things, you are going to see all kinds of things, and please put up your hand, shout, and ask some questions, because we have people here who really know what they're looking at. What I should have done first was to turn off the lights. We need the lights off. Sadly, they don't have a dimmer here. It's dark. Well, okay, I've lots of very young people in here. I just want to know, when do you go out in the night ever when it's got dark? It's good in the winter, and just look up at the stars or the planets? Terrible. I don't actually even know which planets are in the sky at the moment. Jupiter shining brightly. Anyway, we're going to look far beyond Jupiter right now. So here is Heidi. The Hubble Space Telescope, the James Webb Space Telescope is about 1.5 million kilometers away from the Earth and looking out into the depths of space at basically everything is what this slide says.
Yeah, so just for context, so people know, I started working on the James Webb Space Telescope project more than 25 years ago. And at that time, we called this telescope the first light telescope. And that's what this telescope was designed to do, to see the very first stars that ever formed in our universe and the very first galaxies, kind of looking back in time. And that's what that weird shape up in the corner is supposed to designate, the first light emerging from the universe. But because the telescope is so powerful and can see back to the beginning of time, we also can look at galaxies as they're forming over the millions of years, billions of years of the cosmos. And we can look into the galaxies, particularly our galaxy, and look at how stars and planets form over time. And then finally, we want to look at planetary systems, not only planets around other stars, as we said, there's thousands of them now, but even within our own solar system. So all of this science was work that we started planning for, 20 years ago. And so we'll give you a highlight of all these different pieces of the science of James Webb Space Telescope.
And as you say, the very first image, this is just actually, sorry, I forgot this one. This shows how amazingly sharp the vision is with the James Webb.
Yeah, this is 3 different views of the same piece of sky with 3 different infrared telescopes. And I bet you can guess which one is the James Webb Space Telescope. It's the beautiful one that's so sharp and crisp. You can see the stars, and more importantly, in the background, you can see all those dots. And most of those are actually not stars. Those are galaxies. And that is the really powerful capability of James Webb Space Telescope compared to what we had in the past. It's like you can imagine we've just got a whole brand new pair of eyeglasses for humanity to study the distant universe.
It does remind me the first time I got spectacles and I walked out in the evening from the opticians and I looked up at the sky and thought, oh, they are dots of light, those stars. I mean, to me, it's just astonishing, the kind of detail you can see.
Yeah.
Yeah, okay, let's move on. So this is the very first image, or one of the first images we got from the James Webb, is the deep field. And by deep field, you mean looking back towards the Big Bang.
Yes and no. This was the first deep field, but it is not the deepest field. And I think Tom might be able to speak to that a little bit later. But we've gotten even deeper fields now. But this was the first image that we released from James Webb Space Telescope. And what you're looking at here is actually a cluster of galaxies. Every one of those white fuzzy things, anything that doesn't have those sharp lines, we call them diffraction spikes. If it doesn't have a sharp set of lines emanating from it, it's actually a fuzzy galaxy. And you notice there's a whole lot of white ones near the center. And each of those galaxies is composed of billions of stars. And so when you have dozens or hundreds of galaxies, each composed of billions of stars, you have so much mass together in one part of the sky that it distorts space. And when it distorts space, things that are further beyond, that are coming towards us, when they get close to this distortion, they bend and they distort. So if you look very carefully, you see a lot of little streaks. Well,
let me hit the wrong button there.
Yeah, you see a lot of little streaks that are spread out almost in like a circular pattern. Those actually are very, very distant galaxies that have been re-imaged by this cosmic lens created by this cluster of galaxies. So they allow us to, it sort of acts like a magnifier in space that allows us to study the more distant galaxies by studying this cluster in here. And so there's just a lot, I mean, so many galaxies. That's kind of what we thought when we saw this image is, so many galaxies. And a little bit later, we have some measurements of some of those individual galaxies. And we'll talk about that when we come to that slide.
I mean, I was wondering, we've got some young audience here. I don't know if any of the younger ones want to try and count the galaxies. Anything that's not a dot, if you start up in the left-hand corner and work your way down, and if at the end of the session, if you can guess the right number, Heidi will say hello to you. So let's look. So I wanted to show this one. So this is another more recent image, I think, and this is a simulation really that's been put together by ESA. And it's showing, I think, you better tell me, this is the Milky Way we see in the foreground, is it, at the moment, Heidi?
Yeah. Do you,
it looks like
are
it
you
to me.
familiar with this image? Do you know the details of this? Okay, so we'll talk our way through it.
So
yeah, this has got to be our Milky Way galaxy. This is
the animation, which is going to zoom out to what's the Pandora galaxy cluster. But this is sort of how you might see the sky if you just walked out, particularly if you did it in the southern hemisphere.
The southern hemisphere.
Yeah, sadly we don't get this quite good view. And you can see some galaxies, that big smudge and dark stuff in the front. That is our own galaxy. That's where we live. We're looking through it there. So if
that black stuff is dust, just so people know.
And we're going to see more of that.
All the white glow is caused by millions and millions of stars that are all, in the plane of our galaxy. We're looking at it sort of from the side because we're in our galaxy, a big disk. We're in the disk and we're seeing all those stars. But near the center of our galaxy, there's a lot of dust. And that's what that dark stuff is that's blocking out the white glow.
And now we're going to start a journey through to the image of, come on, it's got to work. Can you start the video?
Before.
Oh, here we go. And to me, this simulation it's a pile of different images really illustrates to me just how amazingly sharp focused the James Webb is, because we're just at the moment we're going through our own galaxy, but the cluster of galaxies we're zooming into, which is near the edge of space, is still further away. Have I got the wrong one here? I might have the wrong one.
I think you got the wrong one. You're zooming in on a star formation region here.
Yes.
But it's still beautiful.
I mean, it is just so this is we're going into the fingers, what do you call it? The
pillars of creation.
The pillars of creation.
Yeah, the Eagle Nebula is another term we use for this. And this is a region where stars are being born. And that it's a very up to the top, at the end of those fingers, beyond those fingers, is a group of extremely young stars, just newborn stars. And they are so dynamic. They have a stellar wind blowing out of them, blowing down into a dust cloud. And what those fingers are that you see there are denser regions in the dust cloud that the wind has kind of exposed those dense regions. And at the very tips of those, you can see that there are brighter regions. Those are, in fact, new stars that are being born in that high density dust, and they're being exposed by this wind from the other young stars, the slightly older siblings, if you will, exposing those newborn stars. And so this is a really remarkable area of the sky where we're going to be digging in and studying star formation in real time. And with the power of James Webb, we haven't really talked about what makes it super special. It's an infrared tuned telescope. And so it can sense light that is at longer wavelengths, redder wavelengths than we can see with our eyes, and redder wavelengths than the Hubble Space Telescope can see. And so that red light can penetrate through the dust, and that allows us to get sharper and crisper details of the star formation regions. It's a really super powerful technique. I think if you get an idea of this, if you look down in the lower right, you see there's kind of a triangle that has some red glowing stuff in it. That's we're gonna have to do the whole image then. Oh,
sorry, I'm incompetent on the slide. We'll come.
I just want to. Yeah. You can try starting it if you want, but we may want to move on because we have a lot to cover with the rest of the universe.
Let's go back to your deep space one. Heidi.
Yeah.
Because they're really distant galaxies in that image. And
yeah, this was the same one we showed before, and the little tiny boxes that are picking out individual ancient galaxies, and they're showing them as we can date them by looking at what we call spectral lines, or lines in a spectrum. One of the superpowers of JWST that people don't hear about a lot because they get so excited about the pictures. One of the superpowers is to take a piece of the image and spread the light out into its constituent colors, all the way from blue to red, and then from red to really red and super, super really red. And we look in that distribution of colors for extra light or missing light. And that extra or missing light, exactly the color that it appears at, that tells us what is causing that extra light. So in these 4 different spectra, the lines that have the little spikes, those the red lines are hydrogen. Wherever you see a little red line where that spike is hydrogen, and the blue spike is from oxygen. And what you notice is that that pattern of spikes marches off to the right as we go further and further back in time. And this is the power that allows us to do the actual aging of distant galaxies by looking at those spectral lines, looking at those colors.
I mean, it's a bit like the sound.
For 1 second, I'm gonna one last comment, and then I'm gonna stop.
Yeah.
You are actually looking at molecules in some of the most distant galaxies in the universe. Try to wrap your head around that. These are molecules of hydrogen and oxygen that we're sensing with the James Webb Space Telescope in a galaxy that is like 13 billion years old. It's at the edge of the universe. That's a kind of a mind-blowing thing, and that's what JWST does every day.
Well, it really does blow my mind that 11.3 billion years ago, or 13.1 billion years ago, as it were, a molecule on the edge of the universe shook, its light travelled all that time, and then you just got the the James Webb Telescope up in space just at the right time to catch that light and then to make these pictures. The sheer expanse of time. This is going back 3 times older than the whole solar system is.
Yeah. It's mind-blowing.
Tom, this was one of the first pictures that came out. You were obviously, this isn't your own thing, but when you saw these, did you immediately reckon, wow, I'm going to make some discoveries?
Yeah, I think it's been amazing. Not only that, like JWST is producing pictures that are this crisp and this clean, but it's easy for it. Like the telescope itself is so large and so sensitive that if you wanted to do something like this with Hubble, it would take, hundreds of hours or something of it staring at the same patch of sky. And like Heidi said, this is an afternoon for JWST, that it is detecting these molecular lines right at the edge of the universe. And that we can do this, and that we can do this easily, I think is really amazing. And so I think the discoveries that we're going to make here are going to be really incredible. Like really looking back towards the very first galaxies and those very first stars in those galaxies.
And I think that's one of the things I really wanted to get across, actually, in this panel, is that it's not just the beautiful pictures, it's the science that goes into them. Has anyone actually counted the galaxies yet? You are so slow. I'm going to quickly zip forwards, actually, galaxies are Tom's thing. So I'm going to zip forwards a couple of slides. This is Tom. This is one of the images you released.
Yes, this is. This was So this was one of the first ones that was taken. Actually, this was available the day that they switched the archive to available to download back in July, I think. So we were sat at the top of a hill in Germany, downloading these pictures and just kind of looking at them and going, wow. So yeah, this is NGC 7496. This is a galaxy that's about 30 million light years away or so.
So that's quite close compared to what we were just looking at.
Yes. Yeah, compared to 13.1 billion years of cosmic time. Yeah, this is much closer. So what you can see here is, you're not resolving necessarily individual stars in this galaxy, but you can see the whole galaxy, and you can look at stellar clusters, so groups of stars that are just starting to form. And this galaxy is interesting, actually. So you can see that it has, the kind of distinct kind of cross shape that you get from the JWST mirrors. And that's because this galaxy has an active galactic nucleus. So its black hole is pulling in material, and this lights it up, and it's super, super bright. So it kind of looks like a star almost in the
So
center of it.
that really bright bit in the middle is a black hole.
Yeah, we're looking at the stuff around the black hole that is
Do you know how massive?
Shunning the rest of the galaxy.
Do you know how massive it is?
Off the top of my head, no. Probably about 1 billion times the mass of the sun, or
So
something.
that's all crushed in at the middle and creating all that light, and that's why we're getting those spokes. Those are an optical effect of the way the mirror on the James Webb works.
Yeah.
But that is almost, well, it's outshining large parts of the galaxy. And then you've got all these, it's like a web of light around it.
Yeah. So what you're also looking at here, so this is the MIRI instrument, which is the longer wavelength imager that JWST has on board. So this is looking at the dust continuum. So the black stuff that we saw in the Milky Way earlier lights up here, and you can trace out the kind of spiral arms. They're not very obvious in this galaxy, but they kind of come up like this, kind of up to the left and down to the right. As I'm looking at it, it might be mirrored for you.
That's right. No, we're seeing the same.
Yeah. And also this whole like diffuse filamentary stuff that's going on, that the galaxy, despite being a spiral, is kind of completely filled in by this dust. And you can see, if you look closely, if you squint, you can see that there are these kind of holes in these galaxies, that these are the bubbles that are the kind of things that the Eagle Nebula is. So kind of before JWST launched, we knew of kind of 50 or so of these in the universe. One of the papers that we published, a researcher went in and counted 1,000 of these in one galaxy. So it's really opening up a window into stuff that we just couldn't see before, basically.
I mean, there's towards the top left-hand side, there's this enormous. It's like a cityscape illuminated by bright lights. Those are stars. Are they around the edge of one of these?
Yeah. So these are the youngest stellar clusters. So these are the things that Hubble just couldn't see because it wasn't looking deep enough into the dust to be able to see these things lighting up. But yeah, they're the things that start appearing very red and very bright. Although not all of them, as it turns out, because quite a few of them end up being more distant galaxies. So quite a few of them are in the galaxy, but a number of them are not, actually.
Because I can see some red sort of smudges at the edge of this picture. Those are those out of view, or as it were, galaxies. Are they in the deep distance, or are they stars that have sort of photo bombed this picture? You didn't worry about those, did you?
I would think they're galaxies because they don't have that characteristic spiky structure that you see in the center of this one. So my guess is those are galaxies.
I think a lot of these are background galaxies.
I mean, it's I just, for me, it just keeps on blowing my mind. If you think that it's 100 billion stars in our own galaxy, and then anywhere you look in space, and these give me a sense, Tom, I don't know if you can, or Heidi, if I was to hold my finger out at arm's length, or hold a pin in my fingers at arm's length and put them in front of the sky, how big a patch of sky would something like this be covering?
So this is smaller than you holding your thumb up, I think. Like the point of reference I always think about is the deep field you were showing earlier is probably about the size of your thumb held up at arm's length. That's about, so you have 10,000 galaxies or something in a thumb, and you have that across the whole sky.
And this galaxy, they always have terrible names. Is it sort of the same size as the Milky Way galaxy, or is it smaller or bigger?
This one is smaller. So this is one of the smaller galaxies in
one of the babies. And,
yeah,
I mean,
which is why actually the spiral arms don't look quite so defined. I think is that typically the less massive galaxies don't have such obvious spiral structure in them. They're more flocculent is the term.
Let's just look, because there's another one, pretty similar sort of thing.
Yeah, so this one's NGC 1433, also not a good name.
I'm getting dizzy looking into it, actually. It's like a vortex that I'm looking down into.
This one's quite a strange one, actually. If you look at it, what you see is there's this... The obvious things is there's this small kind of central ring around it. So this is a nuclear ring, and most of the star formation in the galaxy is happening here. And what's happening is you can see kind of these lanes spiraling into that ring. So this is the bar in the galaxy, and that acts to funnel kind of gas and dust and things towards the center of the galaxy. And then that all piles up at this ring, and you get very intense star formation. So you can have, in that ring, I think you have a star formation rate that is basically the same as the entire Milky Way. But then on the outside, this galaxy also doesn't have obvious spiral arms. It looks like there's also this kind of bigger ring in itself. And you can see that it's dotted with all of these red points, which are very young stars being formed. And you can see that there's also all of these kind of holes and bubbles and all of these kind of weird stringy structures coming off that are kind of drifting off from the spiral arms as they're rotating. And so...
Well, I just wanted to ask that. I mean, it might be a really stupid question. In a way, it looks either like a bath plug with all this stuff on the outside, all this stars and dust and stuff being sort of slowly spiraling into the middle, or opposite, this is stuff being flung out by something that's spinning in the middle. I mean, how stupid am I being?
Right.
Very is an acceptable answer.
No, but I think it's more the first one that typically you have things spiraling around the outside, and then that gets plug-holed in towards the center.
The vortex of time. What is it like? I mean, these pictures, I think, have gone around the world in a flash. What's it like being responsible in a sense for these? I mean, you and the team, but you're there doing it.
It's scary. It's also very exciting. And I think there's this, like, the sense of wonder I think that people get when they look at these, and it's hard not to be struck by, like, really how beautiful these pictures are. Like, is exactly the same feeling that we get when we download the data to start with. And there's a bunch of work that we have to do to make them look this pretty. But even just looking at basically the raw data as it's coming down from the telescope itself, you get struck by how amazing and wondrous the cosmos is, I suppose.
Heidi, I want to go back to a couple of the pictures. So tell me, this is these were known before, I think, but we now know a lot more about them because of the James Webb.
Yeah, this is actually a famous cluster of galaxies called Stefan's quintet. And I don't know if you there in Britain watch the American movie It's a Wonderful Life. They had this was an image of these galaxies was used in that movie to sort of be like where the angels lived. This cluster, so it's been around a long time, but what's really cool about this cluster is a couple of things. First of all, I wanted to point out the one on the left. You notice it looks a little bit more sparkly than the other ones. The other ones are smoother and it's sparklier. That's because it's actually a foreground galaxy. It's photobombing the cluster. It's sort of like someone sticking their head in front of the picture when it's being taken. And so it's really not part of the cluster, but the ones in the back are part of a cluster that are literally interacting with one another. And so these bright regions that you see are where the stars, the I don't want to put this. They aren't actually crashing into one another, but they're interacting. The gravitational fields of these clusters are interacting with one another. And so if you go to the next time step, you'll see a longer wavelength, far infrared view. And you notice how much of the haziness goes away, but things pop out at you. And these are the really active star formation regions that Tom was talking about in the galaxies he was describing. And so we're seeing them in this very iconic cluster of galaxies. And just for a moment, look at the background. And again, everything you see in the background, as long as it doesn't have those lines on it, it's a galaxy. And so this is an incredibly rich data set that's only starting to really be explored. But I wanted to actually focus on the galaxy at the top. You notice how the center of that galaxy, just like the one that Tom was discussing, has all those bright spikes because, again, in that top galaxy, there is an active galactic nucleus. And so
that's a black hole again.
Again, exactly. It's a black hole. What we did with the James Webb Space Telescope is we looked at that black hole, that cluster, we looked at that spike right in the center where we know the black hole should be, and we again took spectra of it. And I think you have the spectrum in about 4 slides. So if you kind of jump forward right there. So that's showing you 2 spectra. One of them is sort of the environment around the black hole. And those lines that you see there are iron and argon and neon and sulfur and oxygen. That's all this material that's surrounding in the outermost part of around where the black hole is. But the one on the bottom I found even more interesting because that's a spectrum right at the center of the brightest part. And you see what's highlighted there is sort of a dip in the spectrum of silicates. That's dust.
Sand. So
we're seeing the enshrouding dust that is surrounding that black hole there. And that's very cool. I just want to, people ask this question, and I know Tom's been asked this question too. Do you see the black hole? I thought you couldn't see the black hole because it's black and all the light cannot escape. That's the definition of the black hole. But in fact, what we're seeing is not the black hole. We are seeing all the material around the black hole that is falling into it and getting to a point that we call an accretion disk. And that is what we see. We don't see the hole itself. We see the effect it has on its environment.
It's like a gazillion meteors coming into the atmosphere. This is stuff sort of burning up and getting heated up as it sort of crashes. They're all crashing into each other.
On a much larger scale.
much larger scale. But I love the idea. I mean, this is a point worth making. When you say that you've got silicates there, so that's silicon and oxygen, a bit like sand. But those are the elements which are made in earlier generations of stars. The earliest stars that we were seeing are mostly made of hydrogen, I think, and it takes stars to make the silicates and the carbon and the oxygen that were all made of here.
Yeah, that's right. Did you want to speak to that, Tom?
So this is one of the things that we're really trying to understand with the stuff that I'm working on is really, there's this process of enrichment and regeneration and stuff that as stars reach the end of their life, they explode and they throw out elements into the kind of gas and dust, which then enrich the future stellar populations. So really what we want to understand is, how is the dust affected by the stars themselves? What is the balance between these silicates and these carbonaceous grains and all of these things? Like how big is your dust? How small is your dust? What's it kind of doing? And so this is the kind of stuff that we're really trying to get with these images of these galaxies in particular.
I think what's also amazing, Heidi, I'm not quite sure how the technology of this. So you've got, with these cameras, MIRI and so on, you're getting a spatial picture of a tiny part of space, and then you're somehow zooming in and you're breaking up the colours of the light. For what it's worth, the school has a display of showing how spectra are made just outside in the foyer, if you want to go and look at it, anyone who's here. But you're then sort of focusing in, and then you're on a particular point and you're breaking up the light into its components.
Yeah, that's right. Actually, we have 4 different instruments. And I think, though, I want to mention one particular thing. If you see on the words, it says MIRI IFU. What that IFU means, that stands for integral field unit. But what's important about it is when we take a picture like we see here, every single point in the picture is actually a full spectrum. If you can imagine a third dimension, like, picture, but then extending out of the picture is the full spectrum of every point in that picture. And that is incredibly powerful. So we don't have to just pick one point, put a prism there and spread it out. Pick another point, put a prism there and spread it out. Our camera here, both in the mid-infrared and the near-spec camera, provides us both a picture and the full wavelength coverage for everything in the picture. So this, we are only starting to scratch the surface of the kind of data that we're going to be getting out of James Webb Space Telescope. We're showing you here, I'm just showing you 2 spectra, but every single point in that image, I can show you comparable spectra. And that's a mind-blowing amount of data.
Well, the optics on this telescope must be amazing. I mean, you got these. We haven't actually done the description, but it's made up of a sort of a set of petals, reflecting petals that you launched into space. You packaged them up to go into a rocket. It had to survive the launch process. It's got all these different cameras and analytical tools all on board, and then you send it 1.5 million kilometers into space.
Yeah, I had slides about all that, but in the interest of time, I took that all out. But it's amazing engineering feat, which is why it took us, 20 years to design and craft and test and put this all together before we launched it. We also knew that we would never be able to service it. Like with Hubble, when the mirror was kind of messed up when it was first launched, we sent astronauts up to fix it because it was in low Earth orbit. This telescope, I have a sort of model of it back here. This is, like you said, Roland, it's not serviceable. It had to be perfect. It had to work. And, I'll share with you the whole process of launching this thing on an Ariane 5 rocket, one of the largest rockets humanity has ever made to this date, was so scary. and then it had, like you said, it had to unfold, and there were a lot of things that if the one thing didn't work, the whole project was done. And it took a month for that to all happen. So it was a long month. Waiting for that to happen, for that to all set up, and then we had to focus all the mirrors to all work like one mirror. But like I showed you in one of those early pictures, everything went perfectly, and we have an exquisite tool, more powerful than anything we've ever built before as a species. And so, yeah. It's amazing.
You must have felt a certain amount of responsibility. So this is for me, I have to say, I love all the images, but this is the one that, it's both beautiful and exhilarating in terms of the science.
Yeah, you can tell I like this picture too, right? I got it on the wall behind me. This is, as we talked about with the Eagle Nebula, this is a similar star formation region where you're looking here at just the edge of a bubble, like the bubbles that Tom was talking about in a galaxy, in our galaxy. And again, you have a bright young star up above, several of them that are pushing into this cloud of dust from which those stars were born. And anytime you see a little spike, like you see on the left-hand side over there, you are seeing a place where stars are being born. I went to a conference about the first science coming from JWST, and there was an entire talk just about the details in this particular picture, explaining how much rich information about star formation is buried inside almost every pixel of this picture. And there's going to be probably a dozen PhD theses focused just on this one image. And this is only one of many images. And we're only showing one wavelength here. I don't know, Roland, I don't think we have the longer wavelength image.
So. No.
Yeah, but we have longer wavelength images of the same region where we can actually see inside of those clumps of some of those dusty areas in this picture and see some of those new stars being born. So this is.
See if I can just get this right. The stuff that looks brown on here, that is lots of dust and gas, is it? And that's the stuff that collapses to make new stars.
Exactly.
And why is it so swirly?
Well, because it's a big collection of dust and gas sitting in outer space, and there are these clumps of stars that have certain gravity on their surroundings, and that causes the dust and gas to swirl around. Plus, you have the other stars that have already been born. Each one of them is shooting out jets of material, and those jets are impinging on this dust. It's kind of hard to see in this picture. If we had zoomed in, like in that talk I described, there are places in this nebula where you can zoom in and see jets of material streaming out from some of those tips of material. So everywhere embedded in this dust, new stars are being born, and they're spewing out stuff that is just stirring it all up.
And some of those really bright stars in the blue background above, they were born in this kind of material, is that right?
Hard to tell. I mean, we would have to actually study them carefully to find out if they are part of this cluster or this nebula, or if they're background stars that are just shining through.
I guess I'm wondering why the brown stuff has that shape. Is it being shaped by the older stars in the top part of the picture, or is it?
Yeah, actually, it's being shaped by stars that are up above this picture. You can't even see the stars that are pushing in, that are pushing their stellar wind into this. They're up above this field of view. But like I said, this is a large bubble. And we are zooming in on just a tiny piece of the bubble here in this image.
Tom.
And the edge of the bubble.
And Tom, you were saying then the pictures of the galaxies that you were showing, there are this is the kind of bubble that you were talking about, is it?
Yeah. So these are, these are things that are being shaped by the winds coming out from the stellar clusters, that they push all of this stuff out. And it expands over time.
What I'm wondering is, how much do you talk to the people who take these? I presume that this cluster is, or this star forming system is in our own galaxy. How much do you talk to the people who are studying this and are able to see what individual stars are doing? And then you look at your own pictures and you say, okay, now I have a better idea of why this galaxy looks this particular way.
Yeah, the answer is more and more all the time. That with the observations that we're taking, we are bridging the gap between the stuff that you're seeing at the edge of the universe and the stuff that you're seeing in the Milky Way. Is that we're really now kind of starting to join all of those scales together, and so having people who can tell you about this picture, and then people who can put it in the broader context of the whole galaxy is becoming more and more important. And so our team is kind of 100-ish people now, and it spans people who have worked on the Milky Way for their entire career versus people who have worked on more distant galaxies their whole lives, and everything in between, basically.
Because I think that's one of the things for me which is so amazing about astronomy at the moment, is that the way that, I'm going to skip this final stages, so we'll come back to that maybe. The way, the unity of it all, that when you're seeing the galaxies in the distance, you can now compare them with the galaxies more nearby. You can compare them with our own galaxy, the way the stars and things are formed. And of course, in all of those galaxies, there will be objects like the planets that we have in our own solar system. So I think, Heidi, this was the bit that really amazed me. I had no idea that I thought it'd be a waste of time to look at our own planets, which I thought we knew so well, using the most expensive telescope in the universe.
Well, all I can say, Roland, is I spent 20 years working on this project just so we could look at these things. My program was designed to use James Webb Space Telescope to look at our solar system. And I had, as a scientist for this program, I was selected by NASA in 2002 to work on this program. I spent 2 decades building to this moment. This is, of course, Jupiter. I'm sure you all recognize it, but it looks a little different because it's in the infrared. And you would think that having, had at least 8 flybys of Jupiter with different spacecraft and 2 orbiter spacecraft, including one orbiting Jupiter right now, we would have learned everything there is to learn. But in fact, we discovered brand new things in our first pictures of Jupiter with JWST. I think I just want to point out 3 things. One, the beautiful auroral emission at the northern and southern poles. They're highlighted red in this image because they are longer wavelengths of light. And they are extending up above the cloud tops of Jupiter to quite a large extent. And that was surprising. We had seen aurora with Hubble, but not with this very large extent. So that was number 1. Number 2, I'll just point out the great red spot there. And you're saying to yourself, it's not red, it's white. I'm like, well, that's because we're not looking at visible wavelengths. We're looking at far infrared wavelengths here. And so you're just seeing scattering from high altitude particles before they are absorbed by Jupiter's atmosphere. And that's why it's bright, but it's not red because this is not the colors we would look with our eyes. And the third thing is more subtle. If you look at the right edge of the planet, you see what looks like a ghost edge. I don't know how well your screen is showing this, but can you see that, Roland? What I'm talking about?
I think. Sadly, you can't see where I'm pointing, but at the end of the edge of the white band. Right.
When we first saw this image, we're like, what is that? That edge of Jupiter is supposed to be in shadow. That that should be dark. And there's this bright thing. And I remember some of our non-solar system colleagues saying, oh, the telescope's just out of focus. We're like, no, it is in focus. It turns out that what we think is happening, and this is work being done there in the UK at Oxford and University of Leicester with some of my team members there, we think that bright or red auroral glow that you see at high altitudes is actually spreading all the way around the planet. And it's glowing up in the upper atmosphere, and we can see that glow with the James Webb Space Telescope infrared capability. So it just was brand new. We're like, wow, that's amazing. So we're trying to figure that. So just this one image, there's tons more I could talk about, but this is just a few of the things.
They're all sort of bubbles and blobs and things down to the bottom. I'm thinking, what are those? Or it looks like in the wake of the Great White Spot, there are these sort of little flecks of energy or something.
Those are probably the tops of thunderheads, giant cumulus clouds that are working their way high up into the atmosphere, because to be detected at that wavelength, at that bright, those bright pink spots, they have to be very high altitude, like the top of the Great Red Spot.
Tom, have you got any secrets you can share from your colleagues that you're not supposed to about that aurora?
Unfortunately not.
Let's go back. What's that one? Oh, I think I know why we're looking at this, Heidi. You like this picture?
Yeah. This is an image that actually made me cry when I saw it. You see the beautiful background, but if you look in close, you see a ghostly little shape there and what looks like a bright blue star. That ghostly little shape that, if you look closely, looks like it has rings around it. That's the planet Neptune. And that blue star, that's no star. That is its moon Triton. So if you zoom in, the next time step, I believe, is to zoom in on the planet Neptune. That's Neptune. That is not Saturn. That's Neptune, one of my favorite planets. And it's the reason I cried when I saw this. First of all, I've been waiting 20 years for this picture. And so it was sort of like a life dream. And then the second is the ring system. not only the brightest rings, but if you look closely, there's fainter, ghostly rings embedded in there. And humanity had not seen those rings since 1989, when the Voyager spacecraft flew past Neptune. And since then, we have tried with our largest telescopes on the ground and in space, the Hubble Telescope, Keck Telescope, every telescope, we have tried to see those rings, and they are just too faint. And in this image, a few minutes exposure, boom, there's the whole ring system. So, and those other little bright spots that you see, those are Neptune's moons, and we'll be able to study their icy characteristics. And the planet itself is just filled with clouds, pink clouds and blue clouds, and that tells you their altitudes. I mean, I'm almost speechless because
just remind me, Heidi, was it Neptune that you were studying from one of the Hawaii telescopes when the Voyager was going past?
Yeah, that's kind of one of the tragic moments in my life. But I actually did my PhD thesis using the telescopes in Hawaii to study the clouds of Neptune back in 1988, when we didn't have the fantastic tools we had today. But, I was basically the world's expert on Neptune in 1988. So I joined the Voyager imaging team in preparation for the flyby in 1989, did my postdoc at the Jet Propulsion Laboratory working on the Voyager team. But a few months before the actual flyby, when we flew past the cloud tops, the head of the Voyager imaging team asked me to go to Hawaii again to image Neptune while Voyager was flying by, so that we had a ground truth of what our telescopes were telling us on Earth with the spacecraft. So I missed the flyby that I had been planning for almost 2 to 3 years. I didn't see it. I was on a remote mountaintop, thousands of kilometers away, diligently doing my science. This is what young scientists do, doing the science, getting simultaneous ground-based data. So it was very hard.
But you were seeing it for real in a way, and the rest of us saw just the relay. I think there's something about that immediacy.
With a 4-hour time delay, it takes 4 hours for the light from Neptune to get to the Earth. So I was seeing it 4 hours after Voyager. But yeah, it was important science. And we did publish it as part of the Voyager papers. We included the ground-based data that I used. It was very important to do. But flybys, I mean, they're a moment in like humanity. It's the first time ever we will see this world. And it's a world that I had been yearning for so many years. So it was hard, but that's what the science required. So I did it.
Now, I've actually, I was going to let everyone else ask questions, but I've been hogging them all. Just before, in the few minutes before we end, I don't know if anyone wants me to flick back or forwards to any of these pictures and ask their own questions.
Why don't we flick through them and we'll just say what they are, and then if people want to come back to them, we can talk about them. How about that? So that's Neptune again, the Neptune field. Jupiter, no, go the other direction.
Okay.
Yeah, we're going the other way. Yeah. Okay, Mars. We studied Mars with JWST. Next. We took spectra of Mars that we're looking at the chemistry of the atmosphere and the chemistry of the surface. Next. Titan, Saturn's large moon Titan, we were able to image with the IFU and to see clouds and see markings on the surface of Titan. Next.
Wow,
Chiriclo. This is a little object that's orbiting far beyond Saturn, and it has a ring system. And we actually watched a star cross through the ring system, and that's what the little tracks on the bottom showing you, that with JWST we detected the rings of Chiriclo.
It got blotted out briefly.
Yeah, that's right. The starlight was blotted out by the ring system. Yeah. Next. Planets around other stars.
This is where we started, isn't it, Heidi?
Yeah. So that's a little video. I think if you can, I don't know if you can start the video or not. No, you can't. Anyway, we watched stars crossing in front of their host. We watched planets crossing in front of their host stars, and we see the starlight being blocked out by the planet and its atmosphere, and different colors are blacked out to different levels. And we turn that into a spectrum. So the next time step shows you that chemistry that we get by studying these transits of the planets. And we find carbon dioxide in exoplanet atmospheres. Exoplanet means a planet around another star. So next time step, this is a really cool planetary system called TRAPPIST-1 that has 7 Earth-sized planets orbiting a red star, an M dwarf star, and we're going to be studying all of them. Next time step, these are some spectra of our local planets, Venus, Earth, and Mars, showing you what a carbon dioxide spectrum looks like on 3 different planets that have 3 very different set of characteristics. And so the next time step, we don't know what we're gonna see yet on TRAPPIST. I know that they have started doing that work, but I don't know. I haven't seen the spectrum yet. Have you, Tom? All right, so
I imagine they're keeping it very closely guarded.
Close hold. My point
I tried to ask one of them. They wouldn't share anything.
Yeah, but be patient. As soon as they're confident of their data, it'll come out.
But it's amazing,
from
Heidi,
a single spectrum,
it is amazing. It's amazing, Heidi, that you can look at these distant spots around other stars and say, actually, it's not that there's a solid body or something there. There's an atmosphere, and we can measure it. We can see if it's like our own atmosphere.
Yeah, and just for your audience, I want to emphasize that the pictures of the planets you're seeing there are artists' concepts. What these things look like, even to the most powerful telescopes like Hubble and Webb and Keck, they're just dots of light. We do not have those beautiful pictures. Those are just illustrations imagining what they might look like.
But that's why analyzing the light is so important.
Exactly. We don't have pictures that look like that. We just have a dot of light. And so we need to understand that dot of light. That's why we do the spectroscopy. Next time step.
I think we're going to skip forward. Let's just talk about this one, because your job's not done.
Yeah, this is the thing. I mean, the previous slide shows you why we want to build this. We can only look at a few dozen stars with JWST that are nearby. But if we want to look at hundreds of stars and look for life on them, this is the telescope that we need to build. And we're starting the discussions of that right now here in the US. NASA has put their support behind this. We're going to try to launch it by 2034, but that's a super ambitious schedule. But I think the last time step, I wanted to show you the last picture. I wanted to show you this because the picture on the far left in 2002, that was me when I wrote my proposal to become a scientist for the James Webb Space Telescope project. And that little inset is my bit of my title page with my little baby there, Lucas. The next in the middle is when JWST launched, and that's the same little baby. He's grown up quite a bit. He's there in England. He's studying in London right now in graduate school. And so the next 20 years, by 2042, I didn't put my picture there because I don't know where I'm going to be. But that's the telescope that we want to build for the future. And it'll be for the little kids who are there in the room with you right now, Roland. All those little kids,
Hands
just
up,
like
everyone who
my
wants to do
little guy
this.
was a little baby, and now he's a grown-up kid. That's the little kids.
I put my
now
hand up,
are the ones
Heidi.
who are gonna use them. Yeah.
Tom, you ready for it?
I guess so.
Well, I mean, you're at the beginning of your own astronomical career. You've just got a post at Oxford, so presumably you're looking forward to another 20, 30 years of digging deep into the sky.
Yeah, absolutely. It's a very exciting time at the moment, and I think it's only going to get more exciting with time. We're at a nice point that all of these missions are launching now at the moment, and this amazing data is starting to come down for us to use.
Well, hopefully we can have you back next year and have even more. Heidi, Tom, thank you both so much. Big round of applause, please, for people being really kind. And you can follow James Webb on the social media there. ESA, the European Space Agency, NASA, they have fantastic websites. We basically rob all the pictures from there for these events. So this is only a flavour of it all. Thank you so much, Heidi. Thank you so much, Tom. Bye-bye.